Okay, so we're very happy to have Joaquin here today to tell us something about gravitational index of the heterotic string. Feel free to start.
Okay, yeah, thank you very much for the invitation. I will be talking about some recent work with Yimin Chen, that is a postdoc at Stanford, and Samir Murthy. There we go. Okay, I will begin with some general motivations of why we wanted to study this system. We start with the conjecture that black holes, as seen from the outside, behave as ordinary quantum systems. This is a conjecture that comes from the early 90s, but it has had a lot of concrete realizations from string theory, especially in the context of ADS-CFT, where we can construct black holes in string theory and find what the ordinary quantum system is, and then test this. Well, ADS-CFT is obtained when we consider near extremal black holes and decouple the near horizon to the exterior. Then we end up with ADS-CFT. So what string theory does in these cases is to provide these dual pairs of black holes and quantum systems, but it doesn't really tell us what are the non-perturbative rules in the bulk to quantizing gravity that would lead us to this duality. So the overall motivation is to try to understand what the non-perturbative rules are, because of course we have string theory, but string theory is mostly better understood perturbatively. At least, well, yeah, there's some non-perturbative information we have based on some quantities that might be protected, but we don't have a non-perturbative definition, I think, of what string theory is. From this perspective, the most successful approach has been the gravitational path integral from the point of view of the bulk. This was pioneered by Gibbons and Hawking, but the way we interpret it and the way we apply it has changed a lot over the years. And in particular, so there are a lot of non-trivial calculations that can be done in gravity that produce answers consistent with this conjecture in very non-trivial ways. A particularly famous recent one was the calculation of the page curve, follows the rules of the gravitational path integral. But it's not really derived from any principle in string theory. It's just something we do from low energies that seems to make predictions about black holes consistent with holography, with this conjecture. So what we want to understand, or at least construct, is there some example where we can study how this gravitational path integral emerges from conventional string theory? That's the motivation behind the system we are going to study. Okay. Feel free, of course, to interrupt me or ask any question you have.
One quick question. Do you have any slides? Yeah. I'm not seeing slides for some reason.
Oh, I think I can see the slides, but
let me try leaving the meeting and rejoining. Maybe that'll reboot it.
Oh, yeah. Okay.
Give me just a minute.
Is there any question about the motivation in the meantime? I can answer. Okay.
Okay, now I can see the slides. Thanks.
Now you can see it. Okay, great. Thanks. Okay, so let me begin by explaining this system I'm going to study. So I will be interested in states in the heterotic string. We'll consider the fundamental heterotic string compactified on a 6-dimensional torus down to 4 dimensions. And we'll consider states where the string is compactified along one, this can be done more generally, but we will take one circle of the torus, of the 6-dimensional torus. We will single it out and we will consider the string wrapped around this specific circle with some momentum n and winding w. And from the 4-dimensional point of view, this will look like a point excitation in the non-compact space. And the momentum and the winding will appear as charges of this 4-dimensional particle. So the mass of these heterotic string states with these charges is at weak string coupling, given by this formula. This is just the formulas you learn when you study the heterotic string. QR and Q left are the right and left moving momenta, and NR and N left are the right and left moving excitation number of the string. So this is heterotic, and as you see, the -1 is here, so that means that the right mover is supersymmetric and the left mover is not. Specific class of these states that we will focus on are the double Carl-Harvey states, where the strings are VPS, and this happens when the excitation level of the right movers, which is the supersymmetric sector, is 0, and the left mover excitation number can be anything, in principle, but it's bounded by level matching to be related to the momentum unwinding in this way. These supersymmetric states have a specific mass given by this formula. So it's the right moving momentum squared. And I'm calling it Q because I'm going to interpret it from the 4-dimensional point of view. So these are VPS particles where the mass is fixed in terms of their charge. Okay. So how many of these VPS double Carl-Harvey states are there? Well, at weak coupling, this is easy to count, is the number of left moving excitations for the number of ways to construct a string with a given left moving excitation. And that's counted by, it's the partition function of 24 free bosons. If we compute the degeneracy in terms of the momentum and the winding, then at large charges, it grows exponentially with the square root of n times W. So here tau is it's like a target space chemical potential that couples to this charge, and the worksheet theory will tell you that the partition function in the grand canonical is given by this 24 free boson partition function. So we have a very large number of these VPS states if we take the momentum and the winding to be large, and it grows exponentially. We will be interested not at zero string coupling, but we will be interested at finite coupling. And at finite coupling, we cannot trust this equation anymore, but what we can trust is the index. So if we count not the total number of states, but the number of states weighted by -1 to the f, then this is a quantity that will be unchanged and can be extrapolated to strong coupling. So at the very least, we have this. We have a prediction that there should be this large number of VPS states even at non-zero coupling. And this was computed by double Carl-Harvey a long time ago. So what we want to understand is what is the gravitational description of such states at strong coupling. For the excited heterotic string with large charges, when the energy is bigger than the VPS mass, we expect the string, when we turn on the coupling, to collapse and form a black hole. So the question is, can we reproduce this large degeneracy of VPS states from the black hole picture? How to do it? And when we do this, we run into a problem that I will review in the beginning, which is that the VPS limit of these black holes, the extremal limit of these black holes, is not smooth, but it's singular. At extremality, where you achieve these states that will correspond to the VPS heterotic string, the area of the event horizon becomes 0, and there is an infinite curvature at the horizon. So that's that's an obstruction to this interpretation. And not the interpretation, sorry, an obstruction to using the black hole in a straightforward way to reproduce the degeneracy of the VPS states. There are two contradicting pictures that resolve the singularity, so that's why that was also a motivation of this work. So we want to understand which one is correct, and we will use the gravitational path integral to answer this question. So the two contradicting pictures that are in the literature are, let me start with the one in the right. This is the older one. This one was proposed by Sen in the 90s, and it was actually the first example of a black hole microstate counting in string theory before Strominger and Baffa. Well, okay, to be fair, let me go back. He reproduced the square root of NW, but he couldn't compute the 4 pi, so that's why, in that sense, the Strominger and Baffa was an improvement because they could reproduce the whole entropy. But okay, anyways. His proposal is that as you reach extremality, the black hole becomes small, and then higher derivative corrections leave you with a string-sized black hole that is smooth, but stringy corrections to the geometry are large. Well, I will review this, but you're able to do it because at the horizon, the string coupling is becoming small. So an approximation in gravity where you take into account higher derivative corrections is reliable, as opposed to cases where there are small black holes where the string coupling can become large, and then you wouldn't be able to apply this approach. He didn't find the string-sized black hole solution, but he could show that the entropy will grow as square root of NW with some coefficient he couldn't compute. And this was improved by Double-Car that, in a way, I will explain later. He did find the solution and reproduce the 4π. Okay, but then more recently in 2021, so Sen was in the 90s, Double-Car was early 2000s, and in 2021, Chen, Maldacena, and Witten had a different proposal based on the studies of string theory near the Hagedorn temperature. Okay, I'm also going to explain this. Their picture is that as you approach extremality, the black hole doesn't go all the way to a string-sized black hole, but before it becomes string-sized, the black hole transitions to a string gas, to a self-gravitating string, and then eventually at extremality, you just have a string gas of BPS strings. And they compute the entropy of this configuration, and they also reproduce the 4π square root NW from string theory. So these two pictures are obviously contradicting. So what we want to answer is, what is the right description of the ground state of this quantum system? Is it a string gas or is it a black hole? Okay.
One question.
Yeah.
Yeah. So this so in the left picture, is this the same as the old work by Paczynski about this black hole string transition, or it's a little bit different?
No, it's the same. There is a Horowitz-Polchinski transition. Yeah, the entropy they compute is the entropy of the Horowitz-Polchinski self-gravitating string, and they show that entropy is the same as this one computed from the worksheet.
Oh, I see. Thanks.
Yeah. Okay. So let me review a little bit of these developments. Let me begin with the black hole picture. So this sometimes is referred to as the two-charge black hole because it's a four-dimensional black hole with this winding and momentum charges. Sorry, let me. Yeah. Since supergravity, the heterotic string compactified on T6 can be described by n=4 supergravity, and the bosonic content of this theory is the metric, the dilaton, the B field. We have 28 gauge fields and a lot of scalar moduli. The 28 gauge fields come with 28 charges, and those charges can be interpreted as precisely the left moving momentum of the string when in T6. That's the first 22 components, and the last 6 components can be interpreted as the right moving momentum. So we need to find black hole solutions with these charges. I mean, I didn't write down the action, but there is an action for this theory that's pretty well known. And this problem was solved by Sen using something called the solution generating technique. And schematically, the idea is the following. We start with the Schwarzschild black hole, which is a solution of the two derivative level of the heterotic string theory. And then we apply a duality transformation. And to apply the duality transformation, well, the precise group is 0723 because, well, a string compactified on T6 has a 06,22 duality group. But that's not enough to, when applied to the Schwarzschild black hole, it's not enough to generate a charged black hole. So what he did was to assume that the solution in 4 dimensions has a U1 isometry, which is time translations. And then you can imagine that you're compactifying your heterotic string theory down to 3D instead of 4. And then the duality group would be 0723 instead of 0622. And this duality group that rotates among, let's say, one internal circle and the temporal circle, that group is enough to, from the Schwarzschild solution, generate a electrically charged black hole with mass m and charges q left and q right, where the charges are parameters of this duality transformation and also depend on m, on the mass of the seed Schwarzschild black hole. Okay, so the general solution is kind of complicated, but I written a simple case when q left is 0, or equivalently when n is equal to w. In the string frame, the metric has the following form. So you can see it looks roughly like Reisner-Nordstrom, but not quite. So you have some radial dependent GTT and a radial dependent GRR. And also the dilaton has a specific profile as a function of R, takes this form. The event horizon is located at the point where this denominator vanishes. That happens to be given by this formula. And in particular, you can see that when you take the supersymmetric limit, so when the mass, well, okay, you can see two things. First of all, to avoid the naked singularity, the mass square has to be bigger than QR square over 2. This is the analog of the similar version of Reisner-Nordstrom, that m is bigger than q. And the extremal limit is reached when m is equal, when this numerator is 0, and this is also the supersymmetric limit, okay? But here we see that we obtain singularity, because when the mass is equal to QR square over 2, then R plus is 0, and the singularity is on top of the event horizon. Well, another comment is that if you take the mass to be very large, so that the charge is not important, or you take the charge to be small, then this gives you 2m, that in my units is the size of the event horizon of the Schwarzschild black hole. Okay, the dilaton is defined such that it vanishes at infinity, and it approaches a minimal value at the horizon. So e to the minus phi is roughly 1 at infinity, and then it becomes smaller as you approach the black hole. Sorry, it becomes e to the phi becomes smaller. The string coupling becomes smaller. The value that it takes at the horizon is given by this expression, and you see that at the extremality, the string coupling is identically 0. So no matter what string coupling you have far away, if it's big or small, it will flow to exactly 0 at the singularity. And this is important for sense approach to make sense. Okay, finally, the Hawking temperature is 1/8 pi m. This is the same as the Schwarzschild black hole. And if you evaluate it at the extremality, you get some function of the charge, and this is different from 0. And this should surprise you, because you might think that the extremal black hole should have 0 temperature. And the reason why you can have an extremal black hole with a non-zero temperature is because it's singular. Usually the extremal black hole will have 0 temperature. That statement assumes, of course, that the solution is not singular. Otherwise, you can have more exotic things happening. So the thermodynamics of these two charged black hole, it has the same form. So the mass, as we increase the temperature, decreases. So at small temperatures, this is like Schwarzschild, and Schwarzschild has this, this behavior. And when you approach this, I call this Tmax, is the temperature of the extremal black hole. The mass reaches the supersymmetric mass. Okay, so and here this dashed line is supposed to indicate that you cannot really trust the solution when you're too close to extremality, because of the singularity. The entropy is decreasing also as you increase the temperature, and it goes to 0 at this maximum at the extremality. And we know we are supposed to. Our goal is to show that this actually doesn't go to 0, but instead it saturates at some value that, here is labeled 1, but this the extremal S is intended to mean this 4 pi square root of NW that I wrote before. So this one is the entropy that the string theory predicts. So the entropy goes down as we approach extremality. Here, stringy effects are important, and somehow they should correct this curve so that it saturates at 1 instead of going all the way to 0. Okay, so what are other contributions to the gravitational path integral? This is just one. So I'm going to explain now the solution of Chen, Maldacen, and Witten. As was pointed out, so this involves the Horowitz-Polchinski solution. This is a solution of a self-gravitating string, and it's a gravitational solution with a non-trivial winding condensate. And the idea is the following: we take a thermal ensemble. That's what we are doing. We want to compute the free energy, let's say, of this two-charge black hole or the two-charge heterotic string. So we can interpret it as compactifying time circle with length beta. And let me study first the case of Schwarzschild black hole without charges, just to remind you what the Horowitz-Polchinski solution is. In that case, if you go to this extremal limit and you ask what is going on with the Schwarzschild black hole as I reach this point, the Schwarzschild black hole that was the seal, meaning I'm taking the extremal limit of this side and I'm asking what is going on with the Schwarzschild black hole that was generating this solution at extremality, then the answer is that this Schwarzschild black hole is approaching the Hagedorn temperature. So when the two-charge black hole becomes singular at extremality, it's illustrating the fact that the Schwarzschild black hole you are using to generate this solution is reaching a temperature that is Hagedorn. So close to the Hagedorn temperature, there is a winding mode chi that becomes very light, and this is a string that is wrapping the thermal circle. And it's light because it's a mode that, essentially one way to think about it, it's a mode that would be tachyonic, but it gets a positive contribution from the temperature. And the Hagedorn temperature is the temperature at which these two contributions balance each other, and the mass of this mode is very small. And when the mass of this mode is very light, you cannot just restrict yourself to the supergravity sector. You also need to include this stringy mode as part of your effective theory. And the physics of this mode, well, it's in papers from the 80s, especially Attic and Witten. So what Horowitz and Polchinski did was to recast the theory as a three-dimensional theory with two fields. We have this winding mode, and we also have they also allowed the size of the thermal circle to vary. So we have beta times e to the phi. So phi is 0 away, where we fix what the temperature is, and phi can change as you go inside the geometry, and you can think of phi as a Newtonian potential of the self-gravitating string. Okay, so this is roughly how the geometry looks like. Far away, phi is 0, and the size of the thermal circle is beta. And when we go close to the origin, instead of the black hole, we now have a winding condensate, meaning a region where this winding mode has a non-zero expectation value. And the size of the thermal circle as we approach this winding condensate is becoming, phi is negative, which means that the thermal circle is shrinking slightly, but it's not going all the way to 0 as in a black hole. So this is reliable close to the Hagedorn temperature, and it's an important feature that was, it was known, but it was emphasized in this paper of Chen, Maldacen, and Witten, is the fact that this solution has classical entropy. Usually a QFT solution doesn't have classical entropy because the action will be proportional to beta, because, here we have this time translation symmetry also. So when you compute the entropy, that is roughly 1 minus beta d beta, that will be 0, and there will be no classical QFT contribution to the entropy. In the black hole, this doesn't work because the time circle is shrinking at the horizon, and then this argument is not true. The action the free energy is not proportional to beta anymore, or the log of the partition function is not proportional to beta anymore. But what happens here is that even though the time circle is not shrinking, and even though there is a time translation invariant, what happens is that the mass of the winding mode depends on the temperature, because it has this balance between the tachyonic contribution from the vacuum, let's say, and a contribution from the size of the thermal circle. And because the mass of this mode depends on the temperature, the action is no longer proportional to beta. And you get a non-trivial beta dependence that leads to a classical entropy. And this classical entropy is the thing that reproduces the string entropy, the entropy of the gaseous string. Finally, if you are too close to the Hagedorn temperature, then the classical approximation breaks down and you transition to a free string. But that happens when the temperature is very close to Hagedorn of the order of the string coupling. To this power 4/3, it's not very important. So this is roughly how the thermodynamics looks like for this. Sorry, this is R, but it meant to be beta. It's the mass as a function of beta minus beta h, where beta h is the Hagedorn value. So the mass is going down. So this blue curve is the black hole solution. Then there is this transition to the red curve that is the Horowitz-Polchinski solution. And then at some point, this blob indicates the transition to this free string at very small masses. The entropy has a similar behavior, and the length. This length is the size of the solution. So in the black hole is the size of the event horizon. In the Horowitz-Polchinski solution is the size of the condensate. And this has this behavior that is important because the black hole entropy is the size of the black hole is decreasing as you go close to Hagedorn, as you decrease the mass. But then the size of the Horowitz-Polchinski solution starts growing. The behavior is not monotonic, that's what I'm saying. And then when it matches to the free string, there is an argument interpreting the string as a random walk that tells you that the size of the string should grow with the square root of the entropy. And the Horowitz-Polchinski solution allows you to interpolate between these two pictures. And that was the reason why they introduced it to begin with. Because if you forget about this intermediate region, then you will conclude that there is no smooth transition from the black hole to the string because there are two objects of very different sizes. So that's just to remind you what the motivation was of Horowitz and Polchinski. Okay, so this was the case without charge. Chemadasen and Witten consider the generalization of the self-gradated string to charge configurations, and they essentially do the same trick as Sen. They do these solution generating techniques. You use the duality symmetries of your solution to generate solutions that are charged out of solutions that are not charged. There is some interesting. They have some interesting results that I don't have time to explain, but they're able to find the thermodynamics to all orders in alpha prime of these solutions, and also for the black hole. And this was checked in this recent paper, but okay, I can say more about that if anyone's interested. I will skip that comment. Okay, applying the solution generating technique, they compute the entropy of this charged Horowitz-Polchinski solution, and they get the following answers when the mass is close to QR over square root 2. And this entropy that they get close to this BPS limit matches exactly the 4 pi square root NW in the beginning. Okay, I realize I didn't write it, but there is a relation between QR, Q left, and N and W such that this quantity is precisely the 4 pi square root NW. Okay. And the result in the second line is a different extremal limit that is not supersymmetric, so that's not relevant for what we want to do. Near extremality, the thermodynamics is more reasonable than the small black hole. The mass is approaching the extremal mass as the temperature is going to 0 in this particular way. So in particular now, in the extremal limit, the temperature is not going to some charge-dependent value, it's going to 0 as it should. In the gravitational path integral, the interpretation of this transition is like this. So away from extremality, we have the black hole, which in Euclidean signature, which we use to compute the free energy, has the following topology. We have the thermal circle that is shrinking at the horizon, and these transverse directions that become big and the size of the horizon. And as we approach extremality, there is a smooth transition from this topology to this other topology where the thermal circle is not shrinking and instead is the spatial circle that shrinks. So this topology is roughly like thermal flat space, but here in the tip there is a winding condensate, and this is the solution interpreted as a gravitating string. This picture might look similar if you're familiar with the Hawking-Page transition. It might look similar to that, but it's important to emphasize that that's not the interpretation Chen, Maldacena, and Witten or Horowitz-Polchinski wants to give. What they want to say is that these solutions, interpreted as string backgrounds, they are smoothly connected to each other. This is not very important for what I want to say, but it's an important point in their work, that the proposal is that these two spacetimes are continuously connected as string solutions. Okay.
So it's basically a form of topology change, you're saying. I hadn't appreciated that before.
Yes, yeah, there's a change in topology of the solution.
And this is part of Horowitz-Polchinski. Did I hear you correctly? This has been around for a while, just something I wasn't aware of.
Yes. This is from, so this started by Susskind in something that was called the correspondence principle. Because, well, if you increase the temperature of the black hole, then the black hole becomes a order of the string size, and he was saying that somehow the string should be the black hole should transition to a string. But then Horowitz and Polchinski did this analysis because in this naive picture that Susskind had, there was a mismatch in the size of the string with the size of the black hole, even though their entropies matched. Yes, and so the idea is precisely that these are continuously connected.
Okay, thanks.
Yeah, sure. And another thing they do in the recent paper, to mention a more recent result of Chen, Maldacena, and Witten. Well, the generalization to charged black holes is new. That they didn't do before. And another thing they do is to, for example, they use supersymmetry of the worldsheet CFT to show that this transition cannot happen smoothly for type 2, but it can happen smoothly for the heterotic string. It's just another interesting result of their analysis. Essentially because you can compute the Witten index of the worldsheet CFT, and you can verify that it's not the same on both pictures for type 2, but it is the same for heterotic. Yeah. Yeah, so this is a very interesting results because the motivation is that this might give you some idea of how to understand the black hole microstates using more conventional string states. Okay. So now we can draw a new picture of the thermodynamics. So the blue line is again the black hole. And when we reach to a black hole of string size, instead of going to this funny charge-dependent value of the temperature, it turns around and goes all the way to 0 as it approaches extremality. So this orange line is the string gas. And this is reasonable because if we interpret it as an ordinary quantum system, these VPS states are the ground states. So then the temperature should be going to 0, not to some weird charge-dependent value. So this gives a reasonable picture for the thermal ensemble of a gravitational picture of the thermal ensemble of this system. And then the entropy, well, has a similar behavior. It goes to 0, but then it turns around and goes to this value 1, which is this 4 pi square root NW. So this is, I don't know, resolution 1 on the left in that slide earlier. Okay, so now I will try to go back to the other resolution and see what happens with the black hole picture when you try to use it to evaluate the entropy. And this is based on the new results in this paper, and also there was a paper with some overlap by Ashok Sen and collaborators the same week or the week before. Okay, so what we want to evaluate is the index in the gravitational path integral instead of the free energy, because, well, that's the thing that we can trust from the string theory picture at non-zero coupling, right? The degeneracy in principle is not, we cannot trust it as we turn on the coupling because there can be anomalous dimension that leave certain ground states, but we can trust the index. So what we want to do, the motivation is to see what happens if we try to compute this index with the gravitational path integral. So first I will review some recent developments on how this is done at all. How do we make fermions periodic, or equivalently insert the -1 to the f on the black hole solution? And in some papers, you might find statements saying that you cannot do it. The original black hole doesn't contribute because if the thermal circle is contracting, you cannot make fermions be periodic around the thermal circle because that's a spin structure that wouldn't smoothly continue to the horizon. Fermions should be anti-periodic around any circle that contracts. So the solution was given in this paper in ADS, and then in particular in this paper, we extended this to flat space with Iliesu and Kologlu. And the idea is to add rotation. So we interpret the -1 to the f as turning on an imaginary angular velocity that takes this value, 2 pi I, beta omega is 2 pi I. So the insertion of e to the beta omega j, that would be characteristic of angular velocity in the path in the trace, gets replaced by -1 to the f because of spin statistics. And what happens in this case? Well, to see how this solves the problem, we need to remember what the meaning is of the angular velocity. And the meaning is the following. As we go around the thermal circle, usually we imagine that we go back to the same point if the angular velocity would be 0. But turning on an angular velocity means that as we go around the thermal circle, we also rotate in the spatial directions an angle beta omega. That's one way of thinking of angular velocity. It's like you combine the translation around the thermal circle with the rotation. And when beta omega is 2 pi I, this rotation is exactly 2 pi. So and that's represented by this blue line here. So fields should be periodic if they're bosonic or anti-periodic around this blue arrow. And this is the circle that contracts at the horizon. Here phi is the angular coordinate around the direction of the angular momentum. And what happens is that when this is 2 pi, you can have fermions be anti-periodic in the blue arrow, but be periodic in the red arrow because they are related by this shift. But all fermions are anti-periodic around the 2 pi rotation in the sphere because that circle is contractible even in the boundary. This the equator in the sphere is fermions should be anti-periodic there. So the resolution is that we have fermions periodic under time under going around the thermal circle, but thanks to the rotation in the solution, that's not the circle that contracts at the horizon. And then you are allowed to put this spin structure, this choice of, you're allowed to make this choice of spin structure. So what we need to do is to find a rotating black hole with an angular momentum consistent with this choice of angular velocity, if we want to evaluate the index. So let me remind you how this works for Rice and Nordstrom. The solution is labeled by the mass, the angular momentum, and the charge. And I call it the parameter A. It's just the usual labels in Kerr-Newman solution is J over M. Because omega will be imaginary, this A is natural to take it imaginary as well. So I define this boldface A. And the condition beta omega equals 2 pi I implies that the size of the horizon is Q plus A, and it implies that beta is given in terms of A by this equation. Here I'm just plugging in I didn't write it down, but it's just the standard formulas for Kerr-Newman. For any choice of A, all the solutions have M equals to Q. So whenever you impose beta omega to be 2 pi I, you automatically impose supersymmetry. M is equal to Q. The Killing spinor is integrable. There's a solution. But it's not extremal because the temperature doesn't have to be 0. In fact, the temperature is fixed in terms of A. And this makes sense because I should be able to compute the Witten index at any temperature. it should be independent of the temperature, but it should be able to compute it at any temperature using the gravitational path integral and reproduce the fact that it's temperature independent. So the solution is smooth, and the on-shell action, the important thing is that the on-shell action is temperature independent. So the on-shell action is given by the extremal area. Even though the black hole is not extremal, the area is not equal to Q squared because R plus is not Q, is Q plus A. A is some function of the temperature. And yet the on-shell action gives me the right answer. All BPS solutions of n equals 2 supergravity can be written in this form. This is called the Israel-Wilson form. It can be written as a spatial three-dimensional base labeled by x1, x2, and x3, and then the time circle with some vector omega appear in this form. And this U is called the blackening factor. And Kerr-Newman black hole with beta omega equals 2 pi I takes this form where e to the 2u is the product of h and h tilde, and h and h tilde are harmonic functions. This is just the result of, well, I think it was Todd that derived that this is the most general form a supersymmetric solution can take. An important feature of this solution is that this h and h tilde have two poles at xn and xs. This is the north and south pole. And the extremal black hole corresponds to the limit where xn and xs are on top of each other. In that case, you reproduce something called the Majumdar-Papapetru solution, which is the solution of extremal Reiser-Nordstrom, the one that can be easily generalized to multicenters. Okay, and the separation between these two poles in the x-plane is giving me this rotational parameter. So in terms of pictures, this is the way it looks like in these two different coordinates. In the standard black hole coordinates, the solution is like this. We have the thermal circle shrinking, and the spatial sphere shrinks to the size of the horizon, and we have the north and south pole. And when you map it to these other coordinates, we have these two poles, north and south. We have the thermal circle, and the horizon is actually a line going from the north to the south pole. And if you ask how does the line maps to a sphere, well, the metric is actually singular along this line, but you can show, and this was done by Harder and Hawking, not the cosmology paper, a different paper, where they show that this singularity is just a problem of the coordinates, and well, actually the space is smooth and it's given by this topology. Okay, so to compute the index, we can do the same trick, that solution generating technique, and start with the Kerr black hole now instead of the Schwarzschild black hole with some angular momentum, and apply this duality transformation to generate a charged rotating black hole. And now we will pick the angular momentum to implement the -1 to the f. And well, for big black holes, this choice implies that there is a killing spinor for any temperature, but this is not the case for the two systems. If we introduce the same bold phase A, we get this relation, beta omega over 2 pi I is given by this. And the only solution is that this parameter M is sent to 0, keeping A fixed for this equality to hold. There are other solutions that are not supersymmetric that we studied in another paper with Yiming last year, where, well, I just wanted to mention that other work where we use the same approach to implement the -1 to the f, but we do it for non-supersymmetric theories. Because for non-supersymmetric theories, that index, the trace of -1 to the f is not protected, but you still can compute it, of course, and you can still try to reproduce it with gravity. And so here we have a gravitational prediction of how the black hole microstate should be split between bosonic and fermionics. But okay, anyways, in this case, we want to compute the supersymmetric index, and the only solution is to take this M to be small. And in this limit, the temperature becomes a function of Q, so we have the same problem as before. But it's even worse because now we have a temperature that is fixed in terms of the charges. Well, I should be able to compute the index at any temperature I want. And again, the problem is that A doesn't appear in beta. When you send M to 0, Oh, sorry, here, yeah. When you send m to 0, beta becomes a function of q, but not of a. In the Rice or Nordstrom case, beta was a function of a, so a is determined by beta. And I can pick any beta I want. But for this small black hole, beta is fixed. So that has two problems. Beta is fixed, but it also is a problem because a is completely undetermined. We have this moduli of solutions that with a parameter we cannot fix. Let me mention quickly that the BPS metric takes the same form as this Israel-Wilson. This is the expression. Here I multiply the metric by e to the minus 5 because this is the metric in Einstein frame. That's the one that you should compare with the results of the result I quoted before on Israel-Wilson metrics. In particular, this emblackening factor u is proportional to the dilaton and takes this form. And in this case, this e to the minus u or the dilaton is given by this harmonic function, where again we have two poles. The rotational parameter is again related to the separation between the poles, and the area is proportional to the separation between the poles. So these are things you can check from this geometry. I'm obviously not gonna do it. Okay, the Einstein frame solution, interestingly, is smooth, and the singularity appears in the string frame, and the on-shell action is identically 0. So that means that at the two derivative level, the gravitational prediction from the index is 0, and which is reasonable. So let me mention some problems with these solutions that we will solve in the next couple of slides. So first, I already said it, the index can be evaluated at any temperature, but we found a solution that exists only for a unique value of the temperature. That's weird. There is a modular space of solutions parameterized by the area because the area is proportional to this little a. So this includes in particular the solution where the area is 0. And then we are back to this small black hole that we were trying to get rid of in a way. And finally, the Einstein metric is smooth, but the solution is still singular because the dilaton is blowing up at the poles. Sorry, I should have said that, but yeah, it comes from this expression. So this is the dilaton. This is finite as long as x doesn't coincide with the poles. And what that means is that when you turn on the rotation that implements the -1 to the f, the singularity happens not everywhere at the horizon, but only at the poles. If you don't include the rotation and you take the extremal limit of the solution without the -1 to the f, the singularity is everywhere in the horizon. So when you turn on the -1 to the f, singularity is near the poles. The idea is that since the string coupling is small at the poles, we expect to be able to find the classical solution, including high derivative corrections. And that's what we will do. We will not be able to do this if the string coupling was large because we will not be able to ignore quantum effects. Okay, is there any question?
All good so far.
Okay. Okay, I realize I've been a little slow, but I think that's fine. I don't have to go through all the details. Okay, so here I wanted to argue that these properties that I found for this geometry that compute the index of the small black holes are universal for any small black hole you try to construct in n equals 2 supergravity. N equals 2 supergravity is characterized by, is described by prepotential, which is a function of scalar fields, and these scalar fields are the moduli that are in the vector multiplets. You have nv plus 1, nv is the number of vector multiplets, and the 0th component is because this is a projective, so you can get rid of one of them by a choice of frame. And this function of these scalars specifies the action of supergravity. So there is a formula that tells you how to go from this f of x to the supergravity action. For compactifications to 4D in Calabi-Yau, classically this f of x takes this form whereCijk depends on the geometry of the Calabi-Yau. And the theory has a electromagnetic duality symmetry given by this group that rotates x and f, this vector. Okay, there are similar solutions for an arbitrary n equals 2 supergravity with any number of vector multiplets. The solution is always constructed in terms of these harmonic functions h. Well, there are some equations called the stabilization equations that give you the scalars in terms of the harmonic functions h by solving these two relations. And they also give you this emblackening factor and this vector omega that appears in the metric. I'm sorry, I will go a little fast, but I'll try to make say the main physics points, and I can.
Okay, fair enough.
Yeah, I'll try to make the main physics points. So, okay, so all this machinery that maybe I will skip some of the details. What they take as an input is this harmonic functions h. So you are given harmonic functions, essentially 2nv plus 2 harmonic functions. You put it in this n equals 2 machinery, and the output is a VPS metric, the gauge fields and the scalars everywhere. And the constants in these harmonic functions are the heterotic moduli, and the residues of these poles give you the magnetic and electric charges measured in each center. And this interpretation you get from writing the gauge fields explicitly. Okay, so we can recover using this approach the extremal solution at 0 temperature. This is the original application of the attractor mechanism that also is from the 90s. Extremality is achieved, like I said, by picking this harmonic function to have only one pole instead of being split in two. And the scalars near the pole have a form, this h star and f star, that is universal, and it's fixed by the attractor equation, meaning that this h star and f star are fixed only in terms of the charges and not in terms of the moduli at infinity. In a recent paper with Boruch, Iliesu, and Murthy, we extended this attractor mechanism that worked only at extremality. We extended it to non-extremal VPS solution that we need for what we are doing with this two-charge black hole. And the solution is to split this pole in two, in the north and south pole. We have these two charge vectors at the north and south poles. They are constrained by the fact that their sum has to be equal to the total charge that you measure at infinity. And the difference between them can be interpreted as a dipole moment of the black hole. Smoothness imposes this relation that between beta and the separation between the poles. So this is just like the relation that determines beta in terms of A in Reisner-Nordström. And the solution has an area given by this expression. In the new attractor, what we show is that there is a solution where essentially the finite temperature, imposing that the solution has a finite temperature, gives us these constraints that at the North Pole, the solution is holomorphic, and at the South Pole, the solution is anti-holomorphic. We could exchange the role of North and South. That's not very important. What's important is that either X bar or X vanish at either pole. And the non-vanishing component, for example, in this case, in the North Pole would be X, is equal to the extremal attractor. Moreover, I didn't tell you how to separate the charge into the two dipoles, but we show that the dipole charge is given in terms of also this attractor solution by this equation. And then the on-shell action is given in terms of this intersection product. This is I didn't explain it, but this is the symplectic product between these two vectors. That depends on these dipole charges. And this happens to be equal to the extremal area. So this is roughly how the solution looks like. We have our modular at infinity, and they flow in a way that depends on the modular at infinity. But when you approach the North Pole, they become some universal value for X given by the attractor one, and the X bar is 0. And the opposite happens on the South Pole. And actually, everything else that happens at the horizon is non-universal, meaning that it depends on the value of the scalars at infinity. In the attractor mechanism, the scalars are constant in the sphere, and they are independent of the asymptotic moduli everywhere. But here, this happens only at the poles. Okay, so the small black hole is a black hole which will have zero area at extremality. That means that this intersection product would be zero. And this is the generalization of this. Well, any black hole in n equals 2 supergravity that satisfies this will be a small black hole, meaning that it will have zero area at extremality. And what we can show using these formulas is that any black hole that satisfies this will have all the same three problems that I found for the black hole of Sen. Okay, so all these three properties that I mentioned, that the on-shell action is zero, that regularity gives me a value of beta I cannot tune, and that there is a singularity of some scalar in the horizon that's common to any small black hole you try to construct in this way. Okay, so in the last 5 minutes, I will go over the actual solution of the singularity. Okay, to resolve the problems, we incorporate higher derivative corrections. And here we will make one important assumption that higher derivative corrections come in two flavors. You have F terms and D terms. We will assume that D terms are zero on supersymmetric configurations. This was verified in some specific cases. There is no general proof, but I think it's very reasonable. And this is important because D terms are complicated, but F terms are easy. In particular, for this heterotic string on T6, they are characterized by only this simple correction to the prepotential. Yeah. So, okay, I'm not going to go through the details, but this last part of the talk, the point is to modify this non-extremal attractor mechanism to incorporate this higher derivative correction and show that the presence of these higher derivative corrections removes all the three problems that the two derivative theory had. Okay, that's the upshot anyways. Okay, let me skip this. This is just saying that there is a solution for higher derivatives that have the same principle as before. I can take a harmonic function h, and there's an equation giving me the scalars in terms of these harmonic functions and the metric. That works the same. Then the new attractor works also the same way. The scalars will flow to a universal value at the north and south pole where either x bar or x is zero, and the non-zero component is equal to the extremal attractor, which is derived from these formulas. And finally, the smoothness condition is unchanged, and also the dipole moment equation is unchanged. So most of the equations I showed you before at the two derivative level are not modified when you write them in terms of the attractor value. The thing that is modified is how the attractor value depends on the charge shift, because now the prepotential is different. But once you found the attractor value, then you can apply it in the same equations as the two derivative theory, and you will find a solution that is valid for higher derivatives. This is it's a result of an impressive series of papers by these people. But at least part of it, not the non-extremal one, at least the statements at zero temperature. What we did in the paper with Chen and Murthy was to repeat this at finite temperature, which that's something new, because back then they didn't know how to implement the -1 to the f at finite temperature. Okay, so the upshot is that when you include these higher derivative corrections, this intersection product that was zero for the small black hole, this is the extremal area, now becomes non-zero and proportional to the square root of NW. And this is enough to solve the three issues. For example, if this intersection product is non-zero, so for the small black hole, this was zero, and that means that this term vanished, so there was no relation between beta and A because this term was zero. But when I include this higher derivative correction, this intersection product is not zero anymore, and now I have a relation that gives me a unique value of A as a function of temperature. So I can choose any temperature I want, and for each temperature, I will have a unique solution with a rotational parameter given by this expression. And also the singularity at the poles is resolved. The dilaton is not going to zero, it goes to a small value. Small because it goes to zero if it decreases if I take large charges, it will be small, but it's not zero. And well, I'm going a little fast. So this coefficient C I put a coefficient here, C, in the higher derivative term. There is 1, but I keep it different from 1 just to keep track of what things come from the higher derivative term. So here you can see that even though C is 1, you see that if you would have taken C to be 0, then you would have gotten 0, which is the 2 derivative answer. But C is equal to 1. Okay, we can also evaluate the on-shell action and reproduce the 4 pi square root NW of computed by Doublecard and Harvey using the worksheet string theory. So the summary of the physical picture is the following. If you're computing the thermal ensemble, you do get the transition to the winding condensate and the gas of strings. We believe that the solution of Chen, Magdalena, and Witten is correct in the thermal ensemble. And the solution of Sen and Doublecard applies to the calculation of the supersymmetric index. Although it doesn't work exactly the way they did it, you are forced to turn on a temperature and find these rotating non-extremal VPS solutions that we constructed in this paper that I told you about a little bit. The solution is not particularly small. The size of the horizon is proportional to this parameter A, and this is some function of beta that is not 0. So it's not really a small black hole, but it's a solution where high derivative terms are important to make it consistent. So the answer is that the two solutions are both correct, but they correspond to different observables. That's why they both work in a way. Okay, so that's all. So some open questions is, I think this is a nice setup to study how the gravitational path integral emerges from conventional string theory because, well, this is a case where we have the gravitational path integral that is typical for a black hole that computes the supersymmetric index. But this gravitational path integral with a black hole is computing properties not of a black hole, but computing properties of a string. So this is different than Reiser-Nordstrom, where you can compute the supersymmetric index with a black hole, but in the thermal ensemble, you also have a black hole. I don't know any other example that has this feature. So I think this is a good setup to study this problem. And finally, there are some open questions. For example, is there a self-gravitating string solution that contributes to the index? So is there a Horowitz-Polchinski solution to the index? And the naive answer is no, because the winding mode is removed by GSO projection. So the GSO projection works differently depending on whether fermions are periodic or anti-periodic in time, and the winding mode would not be there for the index. So that means that you should find solutions within supergravity, and that's what we did. Another question is if you can incorporate quantum corrections, meaning corrections that are subleading in the large NW limit. And finally, there are examples where the string coupling is blowing up. So what can we do about those? We cannot apply these techniques because the classical approximation with higher derivatives is definitely not accurate. So I'd like to understand that cases as well. That's it. Thank you. Sorry for going over time.
Thank you.
Yeah, thank you. That was a very nice talk.
Thanks. Yeah.
Any questions?
Yeah. Sorry, I had to rush through the details, but I don't know, maybe it was okay too.
Yeah,
It's
no
all good.
problem.
All good.
Yeah, I have one question. So is there any similar computation or maybe some idea one can try in the Strominger, in the Strominger-Buffer setup? Like I consider some D1 branes and D5 branes as the BPS states in the 40 supergravity.
Yeah, that should. I mean, this is for small black holes. So for the Strominger-Buffer, you don't have to. I mean, for what they do, you don't have to worry about it because that's like the Reiser-Nordstrom case in a way. It's a case where the BPS black hole is big, and the temperature is fixed in terms of the rotational parameter. Well, not fixed. I mean, for a choice of temperature, there will be a unique value of the rotational parameter. So you'll find a unique solution. The solution will be smooth because the size of the horizon is large. And the on-shell action given pi q squared, this is the type of formula that would reproduce. This is for Reiser-Nordstrom, so there are more bells and whistles in the Strominger-Buffer, but this is the type of formula that they will match to the weak coupling string theory calculation of the index.
I see.
But you can ask in their setup, what would happen is, I don't know, maybe you take, I don't know, the number of the momentum. They also have D1, D5, D1 charge, D5 charge, and momentum. And if you take the momentum to be 0, then it will lead to a small black hole. In that case, there should be a similar story as here.
I see.
The complication, I think the gravitational picture will be the same. The picture with the strings might be more complicated because one advantage of this setup is that it uses the fundamental heterotic string alone. So it doesn't have any ingredient that is like D-branes that will be harder to understand. So in a sense, this is, from the string theory point of view, this is the most vanilla, most simpler setup you could have made. Just the fundamental string. That's it. It's
I see.
winding around the circle and moving. That's all.
I see.
So I think that's the motivation for Ashok to study this case also.
I see.
Yeah.
Any other question? If no, let's thank Joaquin again.
Okay. Thank you.
And stop recording.